So now we do maths, and at
We do
5
maths.
we'll have the T, and
Yeah.
we'll circle the day. All right, so.
Okay, so what do you see?
3.
3. Yeah, so I'll click for a bit.
Yeah.
So you see 3. How many of you went 1, 2, 3 in that moment? Anybody? Because your brain, your visual net areas of your brain associated those 3 dots as 3. Young children, before they know number names, do this. They just know. They know quantities. Animals know quantities. They've studied this. There's a lot of work out there being done talking about how we visualize mathematics. For me, that's become an obsession, visualizing mathematics, because I wasn't taught that way. I wasn't taught using this, so we'll talk more about that. So you just saw 3. I'm going to flash another set of dots. Let's see what you do with this one. I'm going to go quick. These are, how many of you are familiar with dot talks? Right? We use them. So I call this my adult dot talk deck. So we're all warmed up. We saw 3. Here you go. I won't let it sit there for very long. See it again? I already see these people flashing with a number. How'd you do that? Anybody out there need a little bit longer with that pattern, and it's okay? So sometimes it takes longer, sometimes it doesn't. We know 3. This just happens when we're young, before we know number names. But this other pattern is what I call cultural subitizing. It's a learned grouping because we subitize up to 4. And beyond 4, it's something we've learned. And we use all kinds of brilliant patterns in our system. 10 frames, you use those, you use counters, you do different visualizations. Neuroscientists tell us the number line is a really effective use of a visual area. So these are the things we focus on. Knowing 3 is subitizing. Knowing 9 would fall in the realm of groupitizing. And groupitizing is a newer term. It's being used at Stanford by a neuroscientist who actually is also in the School of Education. And so they're doing a lot of work with this, and we've been studying it for a while through UCube, through our lab. And it's fascinating that we just know. And then if you also put that 5 and 4 together pretty quickly, that fluency that you have is due to the experiences you've had. How many of you have been at the craps tables recently? So I call it my adult deck. All right, let's try another one. So these are patterns in our world. Oh, and I will mention, some students don't have these patterns. Nothing wrong with them. They just haven't had the experiences. In my high school time teaching, I was fascinated with kids who didn't know dice, domino patterns. They also, I would say, at least 2/3 of my classes in high school, and I taught in a pretty affluent area, they couldn't tell you what a deck of cards consisted of. They could not tell you the structure of a deck of cards. Fascinating, because their standardized testing had questions on decks of cards. That was one of the early, I've been doing this over 40 years, that was one of the early indications I had of something's weird. Is it the testing? What is it? So anyway, here's another one. Ready? It'll go fast, but maybe not as fast as the last one. Still pretty fast, but we're adults, we can handle it. My question for you on this one is, how did you see it? Okay, now here, notice this motioning that's going on around the room. This is one of the look-fors when I'm in a classroom. If I can get gesturing, the neuroscientists tell me that that's when we're playing back here. And we'll get to my whole thing with that in a minute. But so so I saw somebody say, I saw this. You saw lines of 3? Okay, who saw it differently? Yeah.
I saw 4, 2, and then 3.
These 4, and then 2, and then 3? Okay, going left to right? Yes.
And I saw 6, 3.
Ooh, you saw the 6 dice. Ooh, anybody else see the 6 dice now?
Yeah.
Where? I see math, so I was going to call you math. That would be wonderful. Jen Math says she saw the 6 dice. Do you see it? Do you see it on the left or the right? Or the top? Oh my gosh, you're seeing the 6 dice all over the place. Right? And somebody says, I did not see that. I love that, right? Anybody see it differently? So,
I saw the 4 and 3, then my mind almost like knew it was going vertical, so added the 2. But I don't think I explicitly saw those 2.
so you saw, yeah, the 4, the 3, and then the 2. Notice in the Groupitizing realm and others that moved it into the 6 dice are culturally putting it into a pattern. And I love that movement thing that's going on where you think, oh, it looks like that. These are the things that we're looking at in our study with young children currently. And if you're familiar with, we're out and about doing this, I can talk more about that later, but this is a pattern that is not meant to be a set pattern like the previous one. Those of you doing dot talks in your classes, they'll probably look like set patterns. Perfect. Like this. What do you see in that one? Mention it at your table. Tell everybody how you see it and see if you're seeing it in different. See how many different ways you're seeing it at your table. How many different ways? Okay. Okay, count up at your table how many different ways you've seen it. And if you'll raise your hands and just kind of show how many different ways are happening. I see a 3. How many different ways do people see it at your table? I see a 5, a 3, seeing 3s, 3s, 3s. Okay. If we see dots differently, then why are we trying to program our kids with the same mathematics? Right? I was pretty well trained. I majored in applied mathematics. I loved the patterns, and I decided I'd do CS too because punch cards and programming is brilliant. Okay, no, it's not. But I was trained to do this, and I was okay with it. But today, our kids are waiting for something else. For that creativity that Peter was talking about. They're waiting for us to recognize that they're mathematical thinkers. They're ready. So, you want to jump in here?
Yeah. I love how some of you, my team, were seeing, your eyes were behind these walls, because you were trying to see without seeing again, right? And there's no need for you to recognize at a glance instantly. It's also about what image stays in your brain, and as it stays there, how you organize the dots, right? So the line between subitizing and groupitizing, neuroscientists say it's 4, the border, right? But some people were saying 6 because we have the dice in our brain, right? So don't ask exactly where the line between groupitizing and subitizing is exactly, because it might depend on the moment and on the state in which you are. But this is the official definition. It's the ability to recognize small amount of objects up to 4 at a glance. And we know animals. Don't ask me for the reference, because it was late one day. I was watching a Netflix documentary where bees were able to recognize amount of dots. There is even research on how bees recognize 0 as a concept, right? Which is crazy to me with those little brains. So don't say my kids cannot do it, right? Bees are doing it. Everyone.
The bees can.
Bees can, exactly. And then groupitizing, the difference, right? Groupitizing is the ability to combine objects. And I love this word, inconvenient groups, because it's what Cathy was saying. What is convenient might differ from one to another, right? So what is convenient to you? I don't know. And it's like a hack of our subitizing skills. right? Who watched, okay, every time I ask this question, every year, less hands go up. Who watched Rain Man, the movie with Dustin Hoffman? This is great.
That surprised you, didn't it?
Yeah.
Good.
It surprised me because these days I ask him, like, what? Who? Okay, so Dustin Hoffman plays this autistic character, the toothpicks. You remember that scene? The toothpicks are on the ground, and he's like, we're missing 4, we're missing 4, we're missing 4. Of course, it's a movie, but the ability of subitize of that character, which again is a fiction character, is like subitizing much more than 4, right? But then using the structure in the numbers allows us to hack that system and become a little bit like Justin Hoffman, right? And then this is the research from Stanford. I don't know how to pronounce that name, Guillaume, thank you, found that groupitizing skills were the strongest, and this is a big claim, the strongest predictor of math success. Their findings show that strengthening students' ability to groupitize helps them, or helps lessen the effects of income differences on math learning and supports more equal opportunities, right? So if, and of course, as any research in education, the context is important, but if this is a line of research that continues to develop, we were saying groupitizing is rather new as a concept, but if this is like generalizable, like for every kid, then this is a strong claim. Because that means that we have to work on the groupitizing skills of our kids. And since many hands went up when we asked if you to talk about it, I think we're on the same page now on that matter.
So we've become obsessed about this at UQ. Talking to the researchers, we've actually been taking how students go through a little groupitizing assessment and included it in, if you're familiar with an old research paper by Gray and Tall talking about number flexibility. And because that's so important, we talk about number sense, we talk about fluency. What is it that is that number sense and that fluency, right? That's a deep conversation. So we actually redid the Gray and Tall study and, in the Bay Area, and we added groupitizing into it. And we don't have it in this presentation, it's something else that Joe and I are doing. But we found the same thing as Gray and Tall, that number fluency, this ability to combine numbers like you just were, are higher achievers. There's nothing wrong with the lower achievers, they just aren't there yet. And how do we catch them up? That's become my newest obsession. And that's what you're going to experience, what Albert and I planned for you today.
And quoting our friend Jennifer Bay Williams and linking to fluency, as Cathy was saying, number sense, number relationships, and combinations more than general cognitive factors which connect to what we just saw with groupitizing predict student success. So this is not new, but the focus on groupitizing is new. Conversely, lack of number foundations predict later difficulties or disabilities. And not only in math, in general. Right? So if you ask me, more hours of math, yes, please. But then it comes with a cost, I understand.
Okay, I just have to throw out there too, this is my funny thing, because I'm an immigrant to a university working in research. I don't have a PhD, my career has been in public education, like many of you. Teaching, being an administrator, directing mathematics, coaching mathematics. So when I sat in there the first time with the groupitizing research piece that was being said to talk to Joe and I about, I was just looking going, well, kindergarten teachers have been doing dot talks and 10 frames for a really long time, right? It's that wonderful moment where you realize, oh, we've got this, we've known this, we didn't have the research on this, but we've known it. So anyway, cheer for yourselves because we get kids, right?
And we arrived to the elephant in the room. We're in California, there's a new framework, if you didn't hear, yeah, there's a big new framework.
Animated elephant coming up on there.
Yeah, this is the elephant. And we happen to have here a person who collaborated in the framework. So, have you seen this image before? Who did not see this image before? Not yet? Okay, good, now you have. So we're all on the same page. What is
Lots
this?
to unpack here.
A lot. Yeah, this deserves like another hour of PD. We don't have time, but just for you to, or guide your eyes a little bit on this image that summarizes the framework. We have the why we do math In order to make sense of the world, predict what will happen, impact the future, those are the drivers of investigation. The why we do math. So it's about the purpose, right? The how we do math, this is not new, the SMPs. We were talking about the SMPs in the keynote, standards for math practice. A lot of reflection on, okay, how does this translate into what the teachers should be doing with the kids, not only talking about the kids. So that's also not new, but a lot of food for thought. And then the content. And we're using these days, when we do PD about the framework, we're using a metaphor, and I actually did not share it with you, so you can say I don't like it, and then we'll change it. It's the taco metaphor, right? So
Did you say the what?
the taco. Taco?
Taco? Okay, all right, well,
We all love taco.
I'm having a moment, go ahead.
Yeah, the taco metaphor. Okay, I'm gonna try that. So here's the thing. Before these ideas on the framework on content connections and big ideas, and we just saw in Canada they are also talking about big ideas, so this is not only in California, but before this conception of mathematics, you have the ingredients, which are the standards, disconnected. I know you saw the connections as teachers or as math specialists, but many kids and society in general, addition, triangles, quadrados, probability. It's like a bunch of stuff completely disconnected. So lettuce, pico de gallo, tortillas. Ingredients. But who is seeing the taco? Are we seeing that all together these ingredients make a big idea that is the taco? And it can be another food if you prefer, right? But I think the taco is in between, right? In between US culture and Spanish culture. It's just in between Mexican culture. So this is the idea behind making the big ideas, is helping teachers, educators, and ultimately the kids to see the dishes, not just random ingredients.
So I just have to say, who in the audience was on the framework committee? Anyone in here? Do we have any? Can raise your hand. Brian's a writer. Oh my gosh, you guys, thank you. And anybody that was associated with this, California has been waiting. Thank you. Oh my gosh, what a brilliant document. If you've seen as many frameworks as I have, thank you to a Google Power. I don't know, you know? Seriously. And those 4 whats, oh my gosh, amazing. Anyway, carry on.
All right, yeah. So we're gonna come back after the
This
activities.
is fun to unpack, so.
Okay, I'm sorry for this, it's a little long. We can read, I don't need to, I think your English is better than mine. I don't need to read for you. We can read it, this is from chapter 3, and I promise after this we go to activities for the rest of the workshop. We good? Do we agree? Right?
Beautiful.
Yeah, now in front of one of the authors.
Yeah. Thank you, Brian.
You disagree? We hope you agree.
And we've already been doing this morning. The number activity started in the beginning. How many of you are still kind of hooked on the palindromes and you cannot wait to go to date night tonight and do math, right? Seriously, I think we should have a happy hour math party. All right.
Lock the doors.
All right. So you've seen me touching my head. This has happened because of working beside the neuroscientists that do this. Know that me as the educator in the room, I totally disrupt the meetings, but they get over it. They start doing this. And when they're doing this, they're talking about the brain connections, and that's the depth of mathematical learning. And I'm sitting there going, that's a chicken dance to me. It's like, anyway, I'm surprised they still have a job there. But the visual networks in the back of the mind are what I recognize today were not part of my learning. My aunt and my mother were mathematicians from the 20s and 30s, amazing. They gave me toys and things to play with. They were building this. I wish I could talk to them now that I know about this and ask them about it. But I was all right here. How many of you were right here with symbolics? And did you have a lot of language involved? Were you talking about math very much? Nope. So today what we're learning is it's the connections. And it's how do we provide students the chance to build their connections? Because this is their brain. I cannot give them my mathematics, I should not, because it's my goal to help them, to facilitate and help them build their own mathematics, their own connections, their own sense making. So that's what we're going to do today. Play.
Good. Okay, what are these? Okay, it took you what? Half a second? But what do they have in common? Almost nothing. Like physically? What is this? Similar to this. Like, but you see the pattern. You have the idea of, okay, all of them are trees. Your brain, our brain is amazing at recognizing patterns. It's so good that we see patterns where they are not patterns. It's like our brain is not exactly understanding that these are not faced. By the way, I love this one. I can hear it, like the song. So our brain sees patterns much better than we know, right? And even when we don't see, or when we don't think there is a pattern, our brain sees more than one thing. What are these? Same you answered, trees, faces, what are these? Cards, I agree. More specifically? Dots, I agree. Fives. All of them have in common that they are a 5 with the dots, right? So, for instance, imagine I want to do 42 minus 5. One of these representations of 5 helps me better to do 42 minus 5. This one or this one? Probably this one. Because if I see 42 minus 5 as, okay, I can first take away 2 and go to 14. That's my friendly number in this case. And then I get 3 more, right? So this is from our kindergarten program. So number 1 goal in numeracy at the end of K should be that every kid knows numbers 1 to 10 in all their decompositions. Oh no, I'm in kinder and my kids can count to 100. Yeah, congrats, I'm not interested in that. I want them to decompose the numbers. Because counting to 100, just rote counting, that is meaningless, right? So don't get obsessed with the range. That's coming from high school and going down in education, in my experience, has been learning also about, hey, put your goals in a more comfortable number range, think deeply there, and then nobody leaves school without understanding how numbers work. So why we get so obsessed in, no, bigger ranges. There's no need. So I'd rather have my kids understand this deeply at the end of K. I know it's not happening for every kid, but that would be my North Star, rather than rote counting until 1 million, right? And our brain is ready to distinguish the different representations much earlier than we know. Right, so...
I'm just going to say, those of you, I know a lot of you are leaders, we're teachers, leaders, we need to help parents understand what Albert just said, right? Powerful, thank you.
They come to you, I'm an engineer, I think that the algorithm is the only strategy you would be teaching. It worked for me. I'm like, okay, can you do 102 minus 99? Because it's 3, can I see the algorithm? No, but not, I don't want to hear any excuse. I want to see the algorithm you use. No, but in this case, that's what we're talking about, number flexibility.
Yeah.
In this case, we're not using the algorithm or the calculator. Precisely. There's a moment for each tool, right? All right, so we are very good at patterns. Actually, Californian mathematician, he has a wonderful essay called A Mathematician's Lament. Doing mathematics should always mean finding patterns and crafting beautiful and meaningful explanations. We love this quote, and it will help us navigate the activities that we're going to do next. Are we ready?
Yes.
All right.
Activity 1. All right, we're going to play. So what we have for you is activities. So we're going to put some dice out on the tables. If you want to get those passed out, you're going to have some dice, so it's going to get loud. Love it. It's a math party. I mentioned craps. How many people know? We are not gambling. I guess you could. We're going to play with some dice, and we're going to play with our groupitizing and our seeing dots, our studentizing, and we're going to play a little game. And in this game, we're just going to let our beautiful mathematical minds go free, and just see and follow what's going on if we feel it, and talk. The best thing we can do is collaborate. That's real mathematics. Mathematicians, you don't sit in a room and do it all by yourself all the time. You have a lot of conversation. There's a lot of collaboration. So let's get into it. All right. So the first thing I want you to do is grab a dice, and I want you to hold one in your hand. Just one dice in your hand. And I want you to study it. What do you notice and what do you wonder about this dice? Just sit there for a moment and study it. Feel it, hold it, study it. Have you ever paid attention to the structure of the dice? And then have a conversation. What do you notice? Share with your table buddies. So let's just, we're going to move along so we can get playing. Who wants to share an observation? Maybe something you just observed or something you learned from somebody at your table. Who's got something? Yes, in the back.
Over here, 4 minus 1 is 3. And then if you turn it on its side, 6 minus 2 is 4, and 5 minus 1 is also 4.
Okay, fact check everybody. Do you agree? Totally. Do you need it to be said again? Are you okay with it? And you said something at the very beginning that was really important. What did you say first?
It said, opposite sides equals 7. So
Okay, pause there. Confirm that opposite sides equal 7. Anybody have a dice that doesn't work? Okay, what was your next
conjecture?
Like if you hold that, like the 5 and 7 together, and you look at the 4 sides, if you subtract the numbers from each other, they equal the same number. Like 6 minus 3 is 3, 4 minus 1 is also 3. You rotate it, same sort of thing, right? Like 6 minus 1, or 6 minus 5 is 1. 2 minus 1 is also 1.
Fascinating. Okay, so see that I'm obsessed with dice. You'll find a lot of dice stuff on your cute. Thank you. So we could keep going, but I'd like to check for understanding with something important. So I keep going the wrong way. Make a conjecture about, hold the die if you need to, hold the die and orient it in front of you, like the picture, and how do you know what's on the sides you can't see? And then talk to your table partners and see if they agree. Fact check each other. You can even twist it and check again. So what am I doing right now? I'm playing with you in the back. I do this in the classroom. We're going to get back here right now. We're working on mental representations, incredibly important. If I say 2x plus 5 equals 12, what's in your head right now? What do you see? Lunch. Amazing, right? Here's our challenge. We've got to help. So building a mental representation. All right, let's see how good you are at that. Oh, not bad. Where am I? Bernard, I'm having so much fun. I'm Albert. Oh. Can you spot the fake? Talk at your tables, find fakes. If there is a fake. Did you find any fakes?
Yes.
Who can spot a fake? Give us a, kind of use your spatial and tell us where it's located.
Upper left.
Top left? Okay, everybody, look at top left. Is it real or fake?
Fake.
Why? How do you know?
6 and 1 makes 7.
Okay.
It should be opposite. We shouldn't be able to see the 1.
Ah, okay. So we could go on like this, right? This is what I do in the classroom with kids. Doesn't matter their age. It's a great conversation. They love spot and fake. One class of 3rd graders decided to go through the entire bin of dice they had. They were certain some had been made wrong. I was thinking, oh, we should talk. I could do this in high school when we're talking about inequalities, compound inequalities. But anyway, never mind. So here's a little video of the classroom. I'm not a big Google slide deck person. Oh, do we have the audio? Hold it for a few minutes. Yeah, this one. I want you to really study it, really get to know it, feel it. Look at it for a minute. Think about what you notice.
I see that there's 6 squares in this cube of a dice.
6 squares?
That can make a cube. Well, we can see each side has a number on it. If you count by, if you go 1, 2, 3, 4, and you just keep counting and counting, you could see it ends at 6.
So hold the dice. What number's on top? 5? Okay, hold it. See if you can get it to look just like that picture. How many sides can we see? What's opposite 5? If I flip this over, what's on the other side of 5? 2? Interesting. You just told me 6 is opposite 1. 4 is opposite. And 5 is opposite. Uh-oh, somebody's noticing. Your beautiful mathematical brain is seeing a pattern. What's the pattern?
6 plus 1 is 7. 4 plus 3 is 7, and 5 plus 2 is 7. So every single one equals 7.
That is a really interesting detail.
Today's lesson with the dice reiterated the importance of accessible tasks for students. Looking back and seeing all of the students, they were all engaged regardless of their language proficiency or really, what we would traditionally see in their math proficiency.
What engaged them? A model. Getting them back here. We found that to be true in our work at UQ. The more we can get kids back here, the more engaged they are with us as we go forward. They have something to hold and touch and feel, and it's an anchor. Okay, so we need to get to the game. Okay, so we're going to play a game. I call this Keep, Flip, Turn. In its origin, I designed it for 3rd graders, and then something magical happened. We'll talk about that maybe. But so what we're going to do is, there's also a handout for this. I'm sorry, I don't know if we got that out. Yep, you've got it. Okay, so Keep, Flip, Turn requires 3 dice, but it's better with 6. So you might want to have an elbow partner and grab 6 dice. And I'm going to show you the rules. We are going to random number generate, much more fun than a worksheet. We're going to play with 3 add-ins. You've now learned what I now call the rule of 7. And you notice the kids picked it up. Didn't take them long. I did not give them my mathematics. I knew the rule of 7. But I didn't give it to them. I waited for them, and they did it on their own. So Keep, Flip, Turn, what you're going to do is you're going to roll 3 dice. Albert, I just rolled a 4, 1, 2. I love that you're using the dot representation. That makes me so happy. It's going to be your choice what you use. I love that. Okay, what's the sum of my dice, my 3 add-ins?
7.
Okay, I've rolled a 7. Oh, magical. Rolled a 7 with 3 dice. Okay. So now I need to make 10, but I have to follow the rules to make 10. I can keep 1. So I'm going to keep a 4, Albert. Or what do you guys want to keep? Anybody want to tell me what you want to keep? I have a 4, 2, 1. I don't know what you have. Mine's a 4, 2, 1. Keep a 4? Keep a 2. Okay, Albert, we're keeping the 2. So keep goes first. Well, you can do it in any order you want. This is a graphic organizer. I don't necessarily use it with older kids. I use it with younger kids. It's up to you. Okay, so we're going to keep the 2. Which one do you want to flip? And I'll tell you what a flip is. Flip is your rule of 7. So we kept a 2. I love your gesturing. Which one do you want to keep? Or flip, sorry. We kept a 2. Flip the 1. Okay, we're flipping the 1. So when we flip it, what do we get? 6, rule of 7. Now we get to turn. So turn takes out the top and the bottom. You have 4 choices. Can we get to 10? What would I have to turn it to get to 10? The top and the bottom are off limits. You get to do a 2, and we made a 10. Winner, winner, chicken dinner. Okay, no, I did not play craps all the time. I was actually a dealer. That's, well, a craps dealer. It's the way a mathematician makes money during college. Never mind. All right. So, do you need to do another one? You must keep 1, flip 1, turn 1. That's why having 6 dice is really good for kids. They leave their roll out, and then they manipulate the other 3 dice. One of my look-fors is, when do they stop doing that? When do they process it on their own? Not because I've taught them or told them, because they just naturally do. So, keep, flip, turn. Make a 10 with any random roll you get. Go for it. We're going to give you about 5-6 minutes to make 10s. Record your 10s. Record your rolls that you make 10 with. We'll do a little data collection here. Record your ways that make 10 because we want to write them down. Yeah. So there's white books around the room. If you have a roll that you can make 10 of, go up and share it with everybody. A roll that will make 10. You can get a few and go write. We're going to write them on the white books.
Okay, let's make a timeout for a second here. I'm gonna raise my hand because I am learning teaching techniques in the US. You do this in Spain and everybody's like, what is up there? Yeah, the timeout also works. So, here's the thing, as you explore, you can let Xavi know some of the rolls that make 10 with the flip, the keep, and the turn. You know, I spent half of my flight yesterday trying to think about this question. Can you make a 10 with every roll?
What's your intuition?
And where is your intuition going?
What's your gut feeling right now? Yes? Okay,
Yes?
yes?
There's a lot of flexibility in the keep, flip, turn rules.
Let your intuition go. Yes?
So,
I love the Socratic seminar.
okay. Let's raise our left hand if you think yes, every roll can make a 10.
Okay, I gotta do this.
And now let's raise our right hand if you think no, not every roll will make a 10.
Cool.
Maybe you found already a counterexample. Maybe.
And we've got some people saying, time out, I need to work more.
Kathy, you have a question.
Okay, yes.
Can you do it in any order? Can you do keep, flip, turn, or do you need it?
Yeah, with your roll, your choice. But you have to keep 1, flip 1, turn 1.
You cannot flip.
No, that's what, I don't want to do that because I want them to develop their skill. I want them to learn that from each other, not, I hold my mathematics really tight. I try never to give it away. All right, how's it going out there? We've got people putting up their results. Oh no, time out. Pause, the most beautiful mathematical thing is going down on that white book over there. What happened? It didn't work.
You can. I thought I exhausted all possibilities. I would love to see what you've done with this one.
This is a roll, 6, 1, 3.
That's my roll.
And you're not finding a way of making it.
Okay, we've got a, all right, fact checker, collaborator, mathematical collaborator. You say no, you say yes. This is my favorite thing that ever happens.
I can't remember how I did it, but I had the same roll and I ended up with a 5 and 4 on the one.
Okay, wait, that's cool. Same rule, but ended up with a 5, 4, 1. I wouldn't do this with younger kids, but you're adults. What order got a 5, 4, 1? Was it possible?
I don't think it works. Because no matter what I do, if I take the 6 and flip it, I'm back to a 1. If I take the 1 and flip it, I'm back to a 6. If I take the... So if I keep the 1... Yes, but now you can't turn the 6. Because you need the 6, because you have a 1 and a 4, which... Processing.
That's good, that's good.
That's the beauty of this game.
I'm processing. Okay, keep processing. This is real mathematics, convincing each other, right? Getting into, it works. No, it doesn't. Let's chat. I don't have all my video with me today, but third graders, it's the same type of thing. Crazy, right?
Cathy,
Yeah.
we have another candidate.
Oh no, time out. Okay, we need happy hour and dinner. Happy hour for the first task of the day and dinner for this one. We have another conjecture. What's going on, Albert?
They are telling me that this doesn't work for sure.
No. We said that it would work. We could make 10 with all of them.
Ask them.
You guys are seeing it doesn't work? Fact checkers.
We believe this roll does not work, and it's because we know that the patterns of 2 will always make what? 7, right? So we're thinking 7, so the 3s can't work. So if you flip any of them, okay, so let's keep 1. We get 3.
Fact checkers. Here we go.
And then if you flip, what's the opposite of the 3 on the other side? 4. And then if you turn the 3, you only get...
Do you believe this?
You need another 3.
Okay. So your conjecture is 3, 3, 3 doesn't work.
Correct.
Anybody have a question? Burning question now?
How many don't work?
How many don't work?
How many don't work?
Is it always the repeats? You see where my wall of wonder in my classroom, I start writing up the wall of wonder? Because kids get hooked and they can't stop. And we get hooked. So I think we'll move on to our next task. You want to get that set up real? One of the things I want to tell you, at UCubed, we fell off a cliff last summer with this task. This was its original design, and I started showing it to doc students, mathematicians, computer scientists, and we started asking ourselves crazy questions, and we couldn't stop. Still right now, there's questions being asked that we don't know the answer to, right? So on our website, UCubed, on the task page, you will find 5 versions of this task. Do we want to look at that, Albert? Oh, there's some more videos, sorry. You want to see some kids? So you heard the teacher and the coach talking about the class. So when thinking about the importance of groupitizing and the mind, this is what drives a lot of our development of tasks at UCubed. Right now, we're obsessed. We could do this, not so fun.
Yeah, this is opposed to these kind of worksheets, like the amount of additions and subtractions that you're doing with a purpose, right? Thanks to the game. This is what we for research calls productive practice. There's productive struggle. I'm not talking about productive struggle now. I'm talking about productive practice, which is opposed to reproductive practice. This is a worksheet, is reproductive practice. Productive practice is when you have a setting, like this game, that requires you to practice a lot to produce, in this case, an answer to a question, right? And it's like practice in disguise, right? Because the kids don't feel that they are, I mean, the reaction to this or the reaction to the game, completely different, right? It's not magic, not every kid will be like, woo, let's find if every roll makes a 10. No, right? Because that's a state you have to create, but it helps create this state if the task is productive rather than reproductive.
You play to 18, 3 dice, largest sum, 18. We talked about the rule of 7, and then we're making 10s, a really important number for students. And you may have questions, we had questions, some of you might be saying, I want to know how many rolls don't work. I want to know different things. I'm going to skip that one. Okay, so as we took this on, we decided to go to nets. So the middle school version has nets. Not only noticing, is it a net that'll work as a dice? Will it really fold to be a cube? Or will it also, so there's 2 things they have to think about. I think about this along with big ideas. Let's throw in some other things to think about. Will it make a cube, and will it make a dice? And so we have different puzzles, we call them puzzles, where kids can sit there big enough where kids can cut them out if they need to. Nets are hard in middle school. It's hard, this 2-dimensional piece to a 3D piece. So we added the dice fun after the game for that. We also, in our middle and high school versions, we talked about coding. And we went this way with it. Computational thinking is so important in the 21st century. Let's take kids there. Some states are working on this. K-12, California, it's time. So anyway, these are tasks on the site. And it'll be in the slide deck, a link to it. Do you want to add anything?
No, I think that computational thinking, I mean, we have to take some chances to work on it in the math classroom because we don't have a space for now, right? Some people believe computational thinking belongs to another subject. I can agree with that, but for the moment we don't have a space for that. And either science or math needs to take some responsibility on understanding computational thinking. I'm not talking about AI today, and it's not my favorite subject these days, but there's a lot of computational thinking in the world and more to come, right? So we need to train the kids also to understand what an algorithm is. Not with the standard algorithm, but algorithmic thinking, like in a code. And we were saying, because I was telling Cathy, I imagine, remember, half of the flight from New York thinking about this. So I'm like this, using some paper at the end, I turned off the lights, I was thinking, it doesn't work! And the guy next to me was playing? No. So, like, oh yeah, 3D. The moment I saw the 3D in my brain, but then I was imagining a 3D, like a 3D grid, right, with three dimensions, with the 3 dice and all the options, and out of 216 options, which ones will work, which ones won't work, and of course my mind cannot process that. What can we do then? Turn to machines and ask machines to help us on that. And that's what you're trying to do with some computational science.
Yeah, well, one of the Apple CI, computer science engineers, he took this and wrote, generated Python code through chat, through AI, and made a formal proof, because we weren't sure then how many rolls don't work, and how are we going to know? An undergrad that was working with us, he spent all night in our offices. I went in the next morning and the whiteboards were covered with his by force proof of every single roll. Amazing, and he was so proud. Oh my gosh, I loved it. And then the block pieces with the coding are done by one of our other workers. Currently I'm working on, but I haven't finished it, I'm doing a proof inside Excel. Because I'm really curious, kids need to play with spreadsheets. So, and because you can take this into algebra, if you want to go into algebra and mess with it. So it's perfectly poised. Anyway, this is what excites us at UCube. We know we've got something hooked that, and one of the doc students I was working with, who's now at Harvard, decided they were going to the joint conferences, the International Mathematician Conference at that time. It was either in Australia or New Zealand. Yep. Took it down to the conference to share it. So this hooks people. We can hook little kids and ourselves easily. All right, activity 2, we're gonna punt on you. We're gonna stay with dots, but we're going to leave the dice behind. Should I get rid of it?
Yeah.
I'll hand it down. Okay, how do you see it? How do you see it? Think to yourself, what do you see? How do you see it?
So with dots, so
I didn't do it fast, I could have, I didn't. I should have, because that makes you deal with it and not count.
Tell somebody at your table how you see it.
You have a template on your handouts, and you have colored pencils that can help you represent what your brain is doing. So you can use the colored pencils to represent what you see.
So you have 3 rows, how many different ways do you see it? See if people at your table see it differently, you can shade that in, color those.
You see, we are focusing now in case 2. We'll talk later about the rest of cases. Now we're focusing on case 2.
So you're coloring the patterns 3 different ways. No numbers, how do you see it? This is the way we find to lower the floor. We find the engagement. This also stops when you have high achievers kind of doing it fast. They don't do this fast. Often they, for whatever reason, they find this sometimes the most challenging to do it without numbers. So we find that it levels group work when we go to the back first. Visually, go to the back.
actually yesterday, as we were ultimating the details of the slides, I was writing here,
how did you count? And you can do say, no, let's open it more. Like instead of how did you count, it's very intentional to ask, how do you see it? And color it first. Yeah.
And also, if you're counting, that's just, because for me, I'll go algorithmic really fast because that was the way I was taught. I've been spending years in many journals trying to make myself get in the visual area. You'll find it in the classroom too. Some students will not be comfortable getting back here, and they need to. Mathematics is a network. Stronger learning is brain connections. So look at your different ways of seeing it. And then you can go to the second sheet and play with the other side. Flip it over once you see it in different ways. Ready? Okay, this is that moment Peter talked about, moments in the classroom where people don't want to stop. This is what happens. So we've made, Albert has got a little work show for you. One of the things that I look for in a classroom, go ahead.
no, it's a lazy gallery walk.
A lazy gallery walk, you're still sitting.
You're supposed to walk, but it's late, we're going to have lunch in a minute, you don't have energy. So we made the museum come to you instead of you going to...
I love to pause before a problem is done, just to see what you might pick up from others, right? So we are pausing you before you're done, and we are going to have to move on, but you want the mic?
No, you're good.
One of the things I love is, I know that I have real thinking when the work looks different. When the work looks the same, I have to start to wonder whose work is it? My goal is that it isn't mine. Right? I don't want to give away my mathematics. So let the mathematicians show us.
Okay, so I'm not asking the author to speak up, right? This is better.
To read with understanding.
Exactly, it's better for the rest of us, not the author. So the author is not talking. The rest of us, what do you notice? What resonates with what you were doing? We don't have time to go over all of them, but what catches your eye here? I'm sorry, but because it's not the best, the one on the right is not the best quality, but I see some formulas there. It's my high school teacher detector. some ends, right? The world is divided in people who don't care about the colors and just try with these big tools like algebra, or and we were discussing with Cathy, asking people who is more abstract to then represent their ideas is also a learning that we often misrepresent in the classroom, right? It's like, hey, I know you know, but can you show me how you know? Because there's a learning in that. There's an SMP there as well, right? All right, I love the square. Here? Who did that, not this representation, but who used the strategy of seeing a full square?
And if you were filling in dots, adding dots. What's interesting about this is a lot of our students will sit there and go, I didn't think you could.
They think that math is on the page and you can't change it. That's, their creativity is gone, their agency is gone. They think math stays on the page. No adaptations, just do it. And they want to do it their teacher's way. This is what we have to change. This is what Peter was talking about in earlier.
Here we have different representations.
Okay.
Here you have different colors, right? And we were discussing with one table, okay, but what is your constant? That's the key question. What is the same and what changes? The formulas we were talking about, a lot of ends. I know you cannot see them. More. I love this, right? Pointing and clarifying, right? Using different colors to represent this constant, and then these kind of rectangles. Who used this visualization or saw this visualization? With some full rectangles and then some extra dots. Yeah, few of you?
More filling in.
More filling in the square, the full square.
Look at it. Can you see the second row here? Take a look at that one and study it for a minute.
Same but different as this one, right?
Mm-hmm. Similar. Yeah. But do you see? Could you draw in with this? These two mathematicians with their work, could you draw the fifth case using their pattern? These are the types of things we're looking for. Is can I take someone else's work and make sense of it? That's our mathematical practices. Look at someone else's reasoning.
And SMP7, the seeing the structure, right? Which is what we're talking
and the structure.
about.
We're looking at structure. And we're using dots. We're using those visual
I love
networks.
this one, Cathy.
Oh, is that a butterfly?
Yeah.
Beautiful. What is this person showing us? What are they showing us?
The wings, and then the body is the constant.
Reflection.
The symmetry.
Symmetry. Yeah, differently? Okay, I haven't had to do that. We used it in our study, and we watched over time how they would color differently. It was fascinating. When they're coloring unitizing, especially with young kids, we noticed that they only colored in sets of 1s, 2s, and 3s. Never something bigger. Here you can see we had more time. People are coloring bigger arrays, bigger lines of numbers, so that's one of my look fors.
Is that being connected to Groupitizing, what they can?
Yeah, actually, yes, and we saw it in our study. The kids changed in 6 weeks. It was fascinating how they changed. In 18 hours of after school time, they changed. And that's a workshop at UQ. The next one's in March, if you're interested.
Just the power of the facilitative question, truth be told, mine is the middle one there. And when you said, what's the constant, I literally looked at the visual. I appreciate you saying getting away from the numbers, and looked at it, and because of the coloring, something that normally I might skip, I really quickly saw that yellow dot needed to move, that actually just moving that in case 1 would help me see the constant, and it made the math for case 10 much easier too.
Interesting. So this is, we're playing here, and this is actually, we're playing inside of an Algebra 1 to Algebra 2 content level if we push it towards the generalizations. We can do this at any level because kids' generalization just depends on where they are. What's your expectation? How do you want a 5th grader to generalize this? Where do you see the new dots each time? And how would you want an 8th grader or a 10th grader It all comes down, that's what we talk about at UQ, the low floor, high ceiling task. We can take these things lower. What changes is our expectations and what we're pushing towards, what we see that we need to teach.
And you see how groupitizing is helping us make sense of the algebraic expressions, right? We tend to present math as a construct, no, math is a deductive science. It's completely different from any other subject that we teach because it can be deduced, almost all of it, right? So we should put this there is a big debate. Today is not, we were talking about this recently. Today is not about discussing about direct instruction, inquiry-based learning, problem solving, or problem-based learning, all these like types of instruction. But our point is, there is a lot of guidance in discovery. It's not, oh yeah, here you have the task, see you tomorrow, I hope you develop 3,000 years of mathematics on your own. No, that's not discovery. Discovery is with your guidance, right? So you put the activities, this movement that we were doing of asking you, how do you see it, instead of how many, it's a very intentional teaching move that puts the right clue in the right moment and fosters a specific discovery, and then we can move on towards more complex algebraic concepts. And I know some kids can start, like you, some adults can start here, I know, but then how many you're losing on the way, right?
And with
how
this,
communicate.
When I see this, I'll say, well, where's this in the image?
Yeah,
and what does this mean for the image? And start to say, because earlier when I said what's 2x plus 5 equals 12, I don't remember the exact linear equation that I stated, expression, but oftentimes we don't connect back here. But here, we've had 6th graders come up with expressions, algebraic expressions for these dot patterns.
And you don't need n or x, you can have a sentence, right? The early algebraic expression is just a sentence. Twice the amount of squares, or twice the amount of circles plus, it doesn't necessarily mean 2x plus whatever, right?
And this is a whole other, this can go on and on, because notice I asked you, is there a zero case?
Or a
so I'm
minus
playing
1.
with the domain, for those of you that are high school teachers, starting to mess with the domain. And is the domain going to be across the integers? Are we going to limit the domain? Are we going to let it be infinite? What's that going to mean? What does case 2.5 look like? I love to go into animation and make connections to animated movies with this, and the computer systems that do the animation. So there's all kinds of ways we can take this and make it, kids like this.
You can also provide the counters. We had them, but today we didn't. We prefer to give you colors. But a previous step can be giving them you call them bingo.
Oh, the clear plastic bingo chips. I love to have multicolored ones, because for some students, you could pause and have them build it, draw it, write it.
So
those are the connections, and then talk about it, the language centers. This is when the mathematics pops. People say, oh, but this is slower. Yeah, but oh my gosh. Then they get it, and you can't stop them.
Yeah.
They just, and they have this.
Recently I used this metaphor of cooking. I want my kids to do math like my grandma cooks. Right? She's not following a recipe. She just flows in the kitchen. Right? She's 94, daughter, and she was completely unable to record her recipes. I tried a couple of summers ago with the recording. Okay, grandma, what's step 1? Well, it depends. You take this, you take that. Well, if you don't have onion, you can. I'm like, no. I mean, give me ingredients for 1. I am the math person in the family. I can do the proportionality. Can you give me for 1? No, she flows in the kitchen. If she doesn't see this red, she might see the green, or she might see that, and it depends on the situation, right? So we need kids not to follow, but to deduce and be flexible. That's what we're talking about today. And just to summarize, I know we have like 3-4 minutes. I promised we were going to go back to the California Math Framework. I mean, if you didn't read it, you have to trust us when we say this is very aligned with the framework.
Brian,
Seal of approval. But you can think for 30 seconds, and we don't have time to do a turn and talk, but think on your own for 30 seconds. What did we do today? Did we make sense of the world? Did we predict what will happen in some of the activities that we did? Maybe not yet impact the future, but that's That's in the foundations. What math practices have you been practicing, right? What math practices have you been putting into the game? And what contents, right? Have we been exploring changing quantities, taking wholes apart, putting parts together, even shapes, right? When we start talking about squares, and right? Those are the tackles that we are showing the kids here. And now, you want me to go with the big ideas?
Yeah, go with
okay.
big ideas.
So we have a map for each grade has a map. Don't misunderstand the sizes of the circles, right? The sizes of the circles are more of a representation of how many connections is that circle having with other big ideas rather than the importance in a given grade, right? It's also a debate. And then which of these big ideas from kindergarten have we been touching in the activities we've done today? Have we been doing how many? Yeah. Model with numbers? Yeah. Being flexible with intent?
Oh, yeah.
Oh yeah, a lot. Shapes a little bit. Sort and describe data? Not really, but we could.
Yeah, when I do it in the classroom, I collect data. So I do add that teacher move. And I collect the roll data for kids so they can start to see it unfold.
Place and position of numbers? We could. Not really. Bigger or equal? Also we could. First rate, and we could go on. Equal expressions? Yes, for sure. Reasoning about equality? Yes. Tens and ones? Equal parts? Second grade, right? Problem solving, maybe not with measure yet, but.
What if we made this circle pattern dimes? Let's get into money.
And, yeah, that would be dollars and cents.
Yeah.
So activities are always, if they are rich, they open many doors. Your job is to choose which ones, right? In every moment. We could go on and go on, right? But I know we're all hungry, right? It's late for American standards. In Spain, we would wait, but I'm getting used to it. That's true. Oh yeah, I discovered, Cathy was inviting me to see a connection with a famous movie here.
You sometimes see something funny, and what it is I got it passed through, none of the editors noticed.
So I envision a hexagon jumping into my throat on a plane.
There's also in one of our mindset mathematics book, the inspector graphic.
Oh my gosh.
Sometimes I get away with stuff.
And we wanted to finish with the metaphor of the mountain, right? So here we have the mountain of knowledge. On one side, since we don't have time, I'm gonna spoil the interpretation for you. There's the teacher leading at the beginning, right? This is the guided instruction that we were talking about, right? And eventually, of course, kids are collaborating. Eventually, you see how the kids are leading, right? Until we get to the top. On the other side, other approach, it's not a real dichotomy, right? But on the other side of the spectrum, we have a helicopter. We jump into the helicopter. I do, you do. Jump into the helicopter. Go up. Clouds here. We don't see what's going on down there, right? So kids really are unable to replicate this or rededuce that. Oh, my kids don't know their times tables. Yeah, because they see the clouds. If they had built the times tables with you, and that takes more time, as we were seeing today, they would probably, and it's not magic, but they would probably trace back their steps and deduce again. Math is a deductible science. So this is the big idea on this slide is don't be a helicopter teacher. Right? Or avoid as much as possible to be a helicopter teacher. And that, we also fall sometimes, and I don't want to look at anyone because I'm not saying this on purpose for anyone in the room, sometimes we become helicopter leaders as well. Right? No, I'll tell you how to do it. I am the coach, I am the principal, I am the administrator, and I know how to do it. I'm going to tell you. I know that sometimes it's because we don't have the time, but in general, if you can be more of a guide than a helicopter leader, the transformation is easier and more furtherable.
I think, just want to follow up. The Learning Compass at PISA has the Learning Compass, if you haven't taken a look at that. One of the biggest things in there that grabbed me was teacher agency. We talk about student agency. But in my opinion, we will never have full student agency if we don't have teacher agency first. Teachers need to be the artists that they are, and that's also at the foundation of this work.
There's no thinking classroom without a thinking teacher, right? And there's future without a thinking community. And you could keep going, right? So for a thinking society, thanks for coming to Enjoy Thinking, and I think we're going to have lunch in a second, but I'll let Rob finish.
Hey, let's give him a round of applause.